Hi, good morning, and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we do a webinar for essentially for the members of our ZP Developer Zone, but we also use it to answer sometimes technical questions in general. So let me jump straight into it. So every week we do a particular slide, and we show the ZP Academy. We do have a ZP Academy. If you're new to electrochemistry, then check out the ZP Academy. There's definitely a couple of free courses on there that I would essentially recommend. We have our webinars. This is an example. We do this every Thursday, 8 a.m. London time. We have our collaborations. We've had a couple of collaborators over this summer. We offer jobs through it. We have our Developers Own website, and we have our workshops. I'll go fairly fast now because obviously we've got a lot to get through. We are having a workshop in Norway. This is on the 14th to 15th of September. So if you're interested in wearable sensors, obviously CGM, continuous glucose monitoring would be an example, then you can please attend that workshop. We're also having a workshop in India. This is in October. So on the 10th and 11th of October, we have a workshop in India, and then a day's break, and then we have a workshop on the 13th and 14th of October. So if you're in India, and we do have a lot of collaborations going on in India, then please don't hesitate to reach out to us there. Now, this week we got 5 questions. As per normal, we do have a lot to get through, so I'll have to be rather quick. We're going to talk about interferences on chili sensors. I am going to talk specifically about ascorbic acid, gingerol, which is in ginger. The inquiry did ask about garlic as well, and I've missed that one, but what I will answer will help in the garlic situation as well. So we'll talk about interferences on chili sensors. We'll also talk about electrochemical sensing in whole samples without adding ionic electrolytes or without adding buffers, and we'll talk about that. I've also got inquiries regarding pH sensing, the cost of pH sensing, but also the cost around and the technologies around, for example, water testing, using pH sensors. So I will talk about that. Question 4, I apologize, I've only just given it one slide, and the answer is, it's worth a try. So essentially what they're asking in question 4 is, in a glucose sensor or a lactate sensor, we often have a barrier layer, which helps increase our linear range. And the inquirer is asking, can I do the same on a potassium sensor? I think the quick answer is you probably can. And then last question, somebody was asking about flow cells measuring. I think it was just off the top of my head. There was at least oxygen, glucose, and lactate were covered there, and there was also a 4th one there as well. So I'll also cover that. We tried to do this in the space of 30 minutes, so there's an awful lot to go through. So question 1 was around FoodSense. So FoodSense is Zimmer Peacock's commercialization of some technology that originally came from Oxford University, and in some ways we've changed very little. So what you get today essentially is what Oxford University have developed. So they had the original paper, and ZP has, with their blessing, with the Professor Richard Compton, we've commercialized that into something that's usable by food technologists, developers, etc. So let me jump into that. So the first question was, we're really suffering some interferences on our chili sensor. So I am going to answer that. Now, if you are trying to measure the hotness of chilies, you generally try to do it, or one recognized way of doing it is through the measurement of a molecule called capsaicin. Capsaicin is a bit like serotonin, but it's one of these molecules that gives you it binds with receptors and gives you the sensation of hotness. Now, you can do it by HPLC. I'm going to talk about HPLC, and I'm going to talk about the FoodSense. I'm going to talk about how HPLC deals with interferences and how the FoodSense can deal with interferences as well. So you've got 4 ways of doing this. You've got the analytical testing by HPLC. You've got panel testing. I'll just touch on that in a bit, the subjective way. Guessing, this is by far the most common way that's actually happening in the food production industry. And FoodSense. Now, FoodSense intention from the original Oxford paper is really to be a food, well, they would say just measure the hotness of capsaicin, but really it's a food quality system. And what it's meant to do is actually tell you whether something that you're producing is reproducible. So the problem that the vision that we had was somebody's manufacturing a chili sauce, and because the chilies themselves are quite variable, actually you could, blend in your chilies, make your sauce, and test whether you were actually consistent in terms of product. I just want to say hi to Ahmet this morning, Ahmet. Nice to see you this morning, Ahmet. And so the FoodSense is a quality control tool. Now, HPLC is an analytical tool. I will talk about the difference between these two, and I will also talk about specifically about what happens if I measure chili in the presence of ginger. What happens if I measure chili in the presence of ascorbic acid? So we will talk about that as well. So what is hotness? Hotness is this really strange, hotness is almost a sensation / feeling, that it's a subjective experience that people, have. So it's actually quite a tricky market when you're trying to sell something that's quite objective. When you're doing quality control, you're trying to make an objective measurement. And so when people do panel testing or they just do taste testing, they're kind of guessing. That's really a subjective test. They try to make it objective by having panels of people. So they're basically trying to average out all these different responses. But when you have panels of people, it's unless you do it really stringently, it's still, and they call this organoleptin testing. It's, if you have panels of people, you have to well organize it. You have to average everything out. It's an expensive task to do, and quite, in manpower, quite an expensive task to do. So FoodSense at Zimmer Peacock, we are originally, one of our foundings is in the glucose strip market, and we will talk about glucose strips again in a minute. So when you look at our technology, it's a simple little flipping black box. It's got a sensor on the front of it, and it's got an app. So it's really akin to diabetes testing, let's say. Now, FoodSense, I've emphasized this before, is really a quality control tool. It's not the same as an analytical tool. Now, we do have the capability of being an analytical tool, but I will touch upon that quickly. We've obviously read the original science of this. It's interesting that we've got Ahmet online this morning, because what we're doing is, the technique we use is voltammetry, and it's fairly similar to what was done in the original paper. So what we're giving on FoodSense is close to what was originally done at Oxford University. The difference is theirs was a benchtop chemistry experiment or electrochemical experiment, and we've managed to turn it into a user experience. Now, obviously, before shipping these kind of things or in development, we actually bought a whole, we bought pastes, chili sauces, chilies that we blended. I think there's even a chili honey in there when I look at that. So we got a whole bunch of these chili powders. We got all these different sample types, but they very much are chili sample types. Medium curry powder, mild chili powder, some sauces. And we tested them against the HPLC and made sure that we had a good correlation between, I wouldn't say HPLC was a gold standard, but something that's recognized at the moment in industry is HPLC. The reason I don't say it's a gold standard, if you take the same sample of chili and send it to 3 HPLC labs, you'll get 3 different results. So you cannot call it a gold standard. But we have an HPLC. We tested these samples on HPLC. We also tested it on our own system and made sure that we had good correlation. What's important is, now we got a nice surprise one day, because actually some academics at Purdue University, unbeknownst to us, they had bought it, but we didn't know what they were up to. They actually did, as I say, at Purdue University, actually did their own validation of this. So they measured on the chili pot, they measured on the HPLC, they got a correlation, and this paper is in the public domain. I'll make sure that you know where a link to it is. There's a link here. I'll put the links underneath the video. It's in the public domain. And Charlie, the author of this, he really quite liked this technology. He liked it because he could see that, he didn't run the HPLC himself. He had to just send it out for HPLC analysis. He could only do one test per chili because actually it was too expensive to do triplicates. Whereas on our system, he could do triplicates. So he got both a sense of the standard deviation. He was really quite happy with it. And he got a sense of we were correlating with the HPLC as well. So we do get good references from Charlie Rower at Purdue University. So thank you to Charlie for that. When I talk about HPLC, it's not in the abstract. These are pictures I took at our ZP UK location where we actually do have an HPLC. So clearly we do, because we use HPLC sometimes to help us validate our technologies. And if you're going to develop a new technology, it's good to be able to take that sample, analyze it on something that you're familiar with, and then analyze it on the new technology as well, and make sure these things correlate quite well. So when we talk about HPLC, we're not talking about it in the abstract. I'll talk quite quickly. I'm also going to talk about a solution for this particular client as well. So HPLC versus FoodSense. HPLC is about a 50K US dollar instrument. Ours is about 6.5, so it's about an order of magnitude less. When I say high OPEX, high operational expense, so you have to buy the HPLC, you have to keep it in a fairly clean lab. You have to have a probably master's degree chemist to run it. You have organic solvents and you have organic solvent wastes, and you have the columns. The columns are hundreds of euros in themselves. So with us, there's literally no OPEX cost. The operational cost is really quite low. For HPLC, several hours of sample prep, a few minutes of sample prep on the FoodSense. The assay time is at least 20 minutes on the HPLC, and ours is less than 3 minutes. To be honest with you, it's just the cost alone of HPLC, and the high operational cost is it's just too much for most food technology businesses or food production businesses. So it's just the first 2 points which, it's kind of a slam dunk for the FoodSense, but the rest of it's also true as well. Now, what HPLC does give you is what I've termed here data rich, and I will define data rich as well. What the FoodSense gives you is essentially a single number. It's like the glucose sensor in that respect. You get a number, and there's not, but what's happening behind that number is not something that you actually know about. Now, when I say HPLC is data rich, this is a chromatogram from one of our HPLC systems, and what we have is we have signal, and then we have time. And so what's happening is each molecule is essentially passing through the instrument, and as it passes through, we can see the absorptions for different molecules. So what's happening is, you could take a chili sauce, you have to do a lot of workup on it, a lot of preparation of sample, inject it, and then you could see different molecules in that sample. Because the HPLC allows you to do separation as well as analysis. Now with the FoodSense, you just get the Scoville heat unit number, so you lose some of the details behind that final number. Now on balance, FoodSense is a quality control system, so as long as the SHU is consistent, if you do everything the same and everything's done the same in production, then the SH units should also be consistent. So it's kind of meeting its original intention. Now, some people are starting to use it in an actual more of an R&D setting. So they're trying to develop, I think, foods using the FoodSense, which was not its original intention. Its original intention was quality control. If I add lemon juice plus gingerol plus capsaicin into a sauce, do I get a consistent, heat out of it? That's the answer it's trying to do, but people are using it more in a development environment. So I'm just going to talk about, for example, we've got capsaicin. This is the molecule that's generally attributed to giving you the sensation of hotness. This is gingerol. I'm going to point out in a minute, and you can see it now actually. Look how chemically similar these two things are. That's why ginger, sometimes people, I don't know, sometimes, maybe all the time, people think of it as it's actually a spice. And it's because when you look at it, it's actually really similar chemically to capsaicin. And then another molecule I got here is ascorbic acid. Now, if I'm just going to highlight a part of the molecule. Do you see that part of the molecule? That's what allows us to get an electrochemical signal from it, which is the same with gingerol as well. It's this part of the molecule. This part of the molecule and this part of the molecule, you can see they're identical between gingerol and capsaicin. And then ascorbic acid, to a chemist, I would actually understand that these two, this OH and this OH, were really similar to this OH and this OCH3. I know that's a bit of a stretch, and I'm using my kind of, I'm fortunate that I had a degree and a PhD in chemistry and electrochemistry. But these three molecules actually, and I'll show you the data as well, in some analytical techniques are quite similar. But let me, but I will dig into how we would separate these three on the FoodSense. So they will have a raw signal. So the capsaicin has a raw signal, the gingerol has a raw signal, and the ascorbic acid has a raw signal. So when we use, if these three molecules were in a mixture on the FoodSense, we'd end up measuring all three. But I'll show you now how we can deconvolute these three things. Let's talk about a history of the FoodSense. So history of the FoodSense is this. I think we must have launched this about 4 or 5 years ago. We had a chili pot, which became the FoodSense, which was a more sophisticated version. And now actually we've just started the SenseltAll. So the SenseltAll you can think of as FoodSense 3.0. We had a 1.0 with chili pot, then a FoodSense, which was really 2.0, and now we have a SenseltAll, which is really FoodSense 3.0. And I'll just highlight a few things that are different about it. What's different about it is we can actually upload the data. So we get the raw data into our Julie cloud. Now this is significant because at the moment, when people are measuring more complicated mixtures and they say, I get this number, we don't know the root cause all the time of that number. But what we can now do is put the raw data into the cloud. We can still give SHU, Scoville heat units. You can put the raw data through a calibration, which is automatic, and we get Scoville heat units. But now the raw data is in the cloud, which means that somebody can share it with us. And so if you've got results that you're querying, if you run it on the SenseltAll, which is really FoodSense 3.0, the raw data will be in the cloud. And now people like Zimmer and Peacock can look at your raw data and say, okay, I can see an interference. For example, it's ascorbic acid. And then we can adjust essentially the algorithm to get rid of that ascorbic acid. Now, the reason that's important is because when you're talking about the food industry, the things that people can come up with, I think that, there must be a list of hundreds of molecules and ingredients, turmeric, I can think of pepperin, all sorts of interesting molecules. So you'll never know exactly what people are testing. This is just for your interest. If you take a glucose sensor and you put ascorbic acid onto it, but let's say you put a drop of ascorbic acid into blood and put it on a glucose sensor, you'll get a result. You'll get a very high glucose result because it wasn't what the glucose sensor was intended to do. It's intended to measure unadulterated blood and tell you what the glucose is in there. But you can confuse it by putting extra molecules in there. So interference on sensors is not unusual. What's unusual about FoodSense 3.0 or SenseltAll is that actually we'll be able to see those interferences and then advise on why the result is the result, because actually there's ascorbic acid in there, or there's gingerol in there, or there's an interference from garlic, for example. So we've gone through quite a few iterations. We've historically sold 1.0. We came on to 2.0, and actually just recently we've got a new technology called SenseltAll. And the big difference with SenseltAll is all the data goes to the cloud. Once you're in the cloud, that's great because now you can share and collaborate with people a lot more easy. And we can fix things like unusual interferences if it's needed. So I'm going to go question 2 now. So question 2 is actually slightly overlapping with question 1 a little bit, which was, can I test real samples without adjusting for pH or ionic conductivity? So I'll go quite quickly. This is a video I made just this week. And it's really just using the glucose sensor as the illustration that you can take a glucose strip. You can prick your finger. Now, at this point now, I do nothing to this blood other than try to squeeze it out my finger. I didn't really go deep enough here. And then the blood goes straight onto the sensor. That's significant. So the question is, can I run things like non-enzymatic sensors without doing sample prep on them? The answer is yes, you can. Now, I know I'm using an enzymatic example here because I'm using the glucose sensor. But, in fact, I'll talk about potassium sensors in a minute, which are non-enzymatic. So the quick answer to your question is yes, you can. And if you're ever challenged on that, I'm just giving you an example of the glucose strip. That absolutely you can prick your finger, get a drop of blood, wick it up using the capillary of the glucose sensor, and then I got 91 milligrams per DL, and the sort of classic concentration of blood glucose is 90 milligrams per DL or 5 millimolar, depending really if you're in the US or the rest of the world. So the quick answer to your question is yes. Now, I'm gonna slightly expand now and say, look, I'm going to expand and say I'm going to talk about potassium sensors, because when somebody says I want a potassium sensor or I want to use a potassium sensor, there's much deeper questions here, which is, here's a potassium sensor from Zimmer and Peacock. Did you want to use it in a capillary fill mode like this? And so what I mean by a capillary fill mode like this, you take the sensor. This is an awful lot of blood. It's actually just dyed water, but there goes the. So that's quite a simple scenario. I call it mode 1 here, which is you have the sensor, you've put a capillary fill over it, and it just wicks in there. So let's say we were measuring potassium. Potassium is generally in the range 3.5 to 5.2 millimolar. That is a very elegant way of measuring potassium in things like dialysis patients, for example. But it's actually technically one of the hardest ones, because you're putting all the emphasis onto the sensor itself. The sensor itself has to be very reproducible. There's another mode of operation, and I think this mode of operation is used by the iStat, which really started its life in the 80s, and the Epoch, made by Epocal, which is now made by Siemens. iStat, by the way, is made by Abbott. What they do with that is they have a sensor in there, and they have sachets in there. So they don't have our sensor, by the way, I absolutely assure you of that. But they have a sensor in here. It's either what they call an ISFET, an ion selective field effect transistor, or an ISE, an ion selective electrode. It doesn't matter if you're ISFET or ISE. It's the same thing. It's just preference, let's say. So they have a sensing element in there, and they also have sachets in there. And these sachets, I think, the original question a minute ago was, can you test whole blood? And the answer is you can, for example, the glucose sensor. But you have to make quite a good sensor and a very reproducible sensor in order to do that. If you're not able to do that, then you can start giving yourself a bit of a break by putting things like calibration solutions on there, or solutions that prepare the sample. That's kind of mode 2. So in some ways, it's easier and lower cost. It's easier for the customer. Well, it's easier to manufacture, and it's lower cost to do mode 1. It's probably easier to get something onto the market with mode 2, but it's much more expensive, and your shelf life, once you start putting sachets of liquids down, it really affects all your shelf life as well. So then there's mode 2. And then there's mode 3 that I called it here. Mode 3 is, I think this is by Radiometer. It's a desktop blood analyzer. I looked at the manual, and it's got, lo and behold, calibration solutions on it. So I think what they're doing with that one, and I call this one mode 3, is they take the potassium sensor, they put it into essentially a flow stream. They have a calibration solution that flows over the top of the sensor, and then behind it they have the real sample. They almost do a calibration and then read the sample. That's, somebody came to me today and said, I want to make potassium sensors, and I want to make a benchtop instrument, and I've got pumps and calibration solutions. That, from our perspective, is really quite straightforward. The perspective of where you want to read potassium in blood capillary, that is a lot tougher. But I just say that, there are 3 modes of operating a potassium sensor. So, whether the potassium sensor will work or not depends really on what mode of operation you're actually working in. Question number 3. This question started quite simply, but I've also expanded it as well. So, question number 3. First of all, what's the most measured chemical parameter in the world? The most measured chemical parameter in the world is probably pH. I don't know how many measurements of pH in water are made a day or made in urine, but pH is a very measured parameter. First question is how much does it cost to scale the kind of pH sensors that we have at Zimmer and Peacock? And so we can do these sensors at €2 in lots of 10,000 or 50 cents in lots of 1 million. So it gives you a sense of the cost when one scales these kind of sensors. Now at ZP we have a whole technology stack that we call the pH to API. So what does pH? Well, what pH to API means, it's really what we were talking about in SenseltAll earlier on, is actually get the raw data to the cloud. From the cloud, people can actually then call upon that raw data using what's called an application programming interface. So, you know, we have the ZP pH sensor. Now here we have a Android phone with the ZP electronics plugged into it through a USB-C, which is great now, because what it does is it gives us power, and the phone actually gives us connectivity, and that connectivity can connect straight to our cloud, so we can really quickly move the data from the app on the phone actually to the cloud, and then that really gives us custodianship, tracking, quality control, all sorts of useful things. This image is actually quite useful because what this image is showing you is actually electrochemical sensors, including pH sensors, really don't care about the opaqueness of sample. It was just for illustration, it was for a different reason, but we're actually sticking the sensor in milk here. But, you know, if you've got a non-transparent, coloured, dirty sample, for example, blood or milk, pH sensors, electrochemical pH sensors will still operate, unlike optical systems where you'd have to do sometimes filtering, sometimes dilution, but they require some sort of sample prep. What's also quite interesting about pH sensors here is, if you were looking at an optical system, you would have to shield that sample from the ambient light, but that's the beauty about electrochemistry. No need to shield it from ambient light. So we have the electronics, and I'll link to where those are in a minute. In fact, here's the link. So we have something called pH to API. And what we have there is, I'm just going to play this video quickly because I think if people are trying to do things like water testing, you can do something with our sensors which is quite elegant, which is actually put a self-filling mechanism onto them. Now, I think that's quite intriguing in some ways, because the volume of that filling chamber is actually 4 microliters. It could have been smaller, by the way, but standardly we do it about 4 microliters. That tells you that we can make for example, a pH measurement on a drop of blood, no problems. You know, we don't require 1 milliliter or 5 milliliters of sample. We actually require 4 microliters of sample. Electrochemistry can test on sample volumes that are often orders of magnitude less than what was traditionally done in optical systems without any dilution. So if I was to back up a bit, if you need pH sensors from us, then we can on our web store we can sell these at something like 50 cents each. I need to speak a bit faster because I've just had a meeting reminder come in. 50 cents each. We have the electronics. You can plug the sensor into that. This app will actually send the data straight to the cloud, and we can also get into conversations about actually adding value to these kind of sensors as well, because we can put self-filling mechanisms onto them, and that'll also help with the volume being tested as well. I do have to go a little bit faster because I've just had a meeting reminder. Question number 4, and I'm sorry to the questioner. They were just asking, look, if I take one of your potassium sensors, can I put a barrier layer over the top of it? I haven't got time to dig into barrier layers today, but the quick answer is I think you can try it, and I think it'll probably work, but we've never done it. So you know, there's a big you know, catch there. We've never done it, but if you put the barrier layer and just keep it over the working electrode, then I think you should be in good shape. Question number 5, I have to go quite quickly. Question number 5 was really about flow cells, and we have a new flow cell on our website, so I want people to be aware of that. I have a quick video here showing the flow cell in action. So I'm using a hand syringe here. The fittings on this flow cell, by the way, are 1/4-28. This is quite a standard fitting in the world of microfluidics and things like HPLC. We all use the same kind of fittings. And literally you can put your sensors into this flow cell and then just pure hand pushing it through with a syringe. But I'll also talk about pumps in a minute as well. I just want to go back up when I say there's a link here. I'll try and put all these links underneath the video. I've got a meeting immediately after this, but I'll try and put the links in underneath the video afterwards. These images are also on the website, and underneath that link showing you that actually this is a modular system, and you sort of plug the sensor in and then you can clamp down on top of it. You don't need to have these electrodes in the flow cell you can just bring them to the flow cell and essentially clamp them in place. I have again links to this, and I'll try and put it into these videos. This flow cell has what they call a LEMO 4-pin connector. So that LEMO 4-pin connector is important because that LEMO 4-pin connector will plug into one of our anapots. So our glucose sensors will work with this, the oxygen, the lactate, the pH will work with it. If you're going to use a pH sensor, use this particular part number because it's made on a ceramic and it will fit into the holder correctly. This is the anapot. And that's where you'll actually plug in the flow cell. So that's the electronic connection for the flow cell. In terms of pumps, I have no affiliation with this pump company, but it's just to say that we do have one of these pumps, and this pump's kind of useful because what it does is it has both a switchable valve on it, which means has the pump, which is syringe driven, has a switchable valve. You can pull from calibration reservoirs. You can also pull from a sample reservoir as well. So that's something that we do play with. I have no affiliation with this company. It's just to give you a sense of what we're up to. So I apologize. It's 8:31. I have to jump into a meeting. But question number 1, interferences on chili sensors. We need to upgrade the person to a FoodSense 3.0. So we're getting a questioning coming in, and that's why I wanted to have this webinar, because the person questioning, we're going to upgrade them to what's called a FoodSense 3.0. No issues there. We just need to have an email conversation about that. Discussion on electrochemical sensors and whole samples. Yes, you can test whole blood in electrochemical sensing. pH at scale, things like 50 cents for a million sensors, or 50 cents each for a million sensors. You can try that barrier layer on potassium sensors. I think it'll work, but we've never done it. And then the flow cells, hopefully there's a few links that I'll put underneath the video when I finish this, and that hopefully that will help. So with regards to the inquiry about the interferences, yes, you're on a FoodSense 2.0, and we'll put you onto a FoodSense 3.0, and that will then allow us to see your raw data and understand the sources of the molecules that are causing your signal to be where your signal's at. So I apologize, I have to run to my meetings, but otherwise take care, and I will speak to you all soon.